Okay, hello, my name is Marcin Wielgus. I'm a software engineer at Google, and for the last 2 years I have been actively working on the Kubernetes project, and today the Kubernetes will be the topic of our presentation. But before we actually start, let's move in time to the 18th or 19th century. At that time, a big part of the world has already been discovered, and for good and for bad, trading posts were established in even quite remote areas. Putting all of the moral aspects aside and simplifying a lot, we had coffee in South America, tobacco in Central, spices in India, and the strong need to transport these goods from point A to point B. The transport on greater distances could happen only on ships. Like this one, with sails, cannons and marines. Most of you seeing such a picture immediately think about pirates, treasures and great epic naval battles. The same do I, but for a moment, let's focus on some other aspects of the story, on the cargo bay. Here is a cross-section of a sample ship. You can see, maybe the last rows don't, but try to use your imagination that we have here barrels of special stands, big boxes, small bags, big bags. Little sides, lots of stuff that needs to be securely placed and fastened, and ideally taken care during the transport. I can guess that it could take quite a while to properly load, balance, and later unload a single ship. Even more, if you had tons of goods to transport and multiple big ships. That's how the situation looked 100 years ago. What does it look like now? If you take a look at the current long-range transportation industry, it's dominated by the containers. No one bothers about bags or barrels. To operate at the global scale, companies like Mars need to have a standardized way to package the cargo, like these containers on the picture. They come in well-defined sizes and can be easily stacked together. The content on one container doesn't interfere with the other. The containers allow us to utilize ships in a great way. The ships can carry more, they can be fast loaded and unloaded, and containers are convenient both for the transportation company as well as the container owners. However, to make the best use of the containers, you need the proper infrastructure, like cranes that are specially designed to load and unload them in a fast way, trained operators to properly balance the ships so that the fully loaded ship doesn't go upside down. You need well-designed ships with appropriate cargo bays and sometimes special wiring to connect containers to electricity, and so on and so on. You may ask why I'm talking about ships and cranes. Well, if you think about it, there is a large number of similarities between cargo and DevOps worlds. You, same as the cargo company, want to have your stuff loaded as fast as possible, packed as efficiently as possible, and delivered to the user without much of interventions. At Google, we noticed the benefits of containers a long time ago. And we have been using them for the last 15 years. And we realized that having just containers doesn't work if you have hundreds of thousands of machines. You simply cannot go and manually start them on individual boxes. You cannot go and check whether there are still up and runnings. And obviously no human is able to plan where to put these millions of containers so the machines are properly utilized. Not to mention connecting these thousands of containers together. So we built an internal system called Borg. Borg is great. It solves all the mentioned problems, but on the other hand, it's so complex and so tightly fitted to the way Google operates that basically no one can use it outside of the company. After these 15 years, we strongly believe that the containers are great and everyone should be used to them efficiently. So, with a couple of our partners, like Red Hat or CoOS, we created Kubernetes, and we launched the first version back in 2015. What's Kubernetes? Kubernetes is a system for automatic deployment, scaling, and management of clusterized applications. is 100% open source. In fact, we open source it to such an extent that neither Red Hat owns the code. With the release 1.0, we donated all of the source code to a newly created cloud-native computing foundation, which is run in a similar fashion as Linux Foundation. So no individual company can dictate the roadmap or close the project. It's a joint effort and everyone is invited. And we really mean so. We run about 10 to 15 special interest groups per week to ensure that all voices in the community are heard. Kubernetes runs on all environments, on private cloud, public cloud, as well as bare metal. It can be set up with just a couple of command lines. It supports Docker, as well as other container running environments like Rocket. It focuses on application, not machines. Usually, the best idea to explain a topic is to give an example. So, let's build a gossip site. I'm not sure if you happen to have such a thing in Russia, but here is an example of what this thing looks like in my home country. You see a lot of pictures and news critical to the future of mankind, like this one. Justin Bieber just landed in Krakow, my home city. Or below, the update on the Prince Harry's girlfriend list. Gossip or not will make our architecture quite standard. So we will have a bunch of front ends to show the pages to the user. We'll have backend servers to perform business logic, whatever this business logic is in terms of gossips. We'll have web servers to provide images and database for gossip and discussion boards. On top of them, there will be a set of L7 load balancers. Here, the diagram shows more or less what does it look like. The requests go to the load balancer. Then, based on the URL, they are routed either to the image serving servers or to frontends. Frontends talks with backends, and backends talk to the database. So, quite simple and standard. Let's see how Kubernetes helps with implementing such an architecture. Let's start with pod, the basic concept of Kubernetes. A pod is a set of containers that are run together on a single machine, share volumes, have the same IP addresses, and can communicate easily via localhost. What does it exactly mean? Why pods are better than solo containers? In our gossip example, we have a server that provides these Justin Bieber images to the user. One of many possible solutions contains two elements. Some component that pulls the images from the central repository and stores them locally in a shared directory, and a web server that serves the images on demand from the local disk. None of these components make actually sense without the other. In theory, you could put both of them into a single container, but it would make a lot of things harder, like what to do when the file pooler crashes. Or should it restart both programs or just one? Should you have some custom script to control them? How would you do the upgrades? Having the containers a bit separated definitely helps. One important thing to mention is the IP addresses. All pod containers are accessible within the cluster using the same pod unique IP addresses that is provided automatically by the Kubernetes. You create a pod and it gets IP, like DHCP, but for containers. With each pod having a unique IP address, you don't need to worry about machine ports anymore. You can have 20 pods on a single machine listening on port 80 and it will be fine. What else in the pod? The main part is the list of containers, and each of them is specified by the image to execute and the command. There is also an expected amount of memory and CPU that the container will use. There are volumes that Kubernetes can automatically attach, like NFS, iSCSI, Cloud Drive, or simply a directory on your local machine. On the pod level, you can specify among many other things what type of machines it should run on, whether it should be close to some pods or opposite, anywhere but not on on the same nodes as the other pods. For example, if you run 3 instances of your servers for high availability, you don't want them to be placed on the same machine. The information specified in the pod is used by Kubernetes to place the pods on the best possible location. You remember this picture with cranes? The cargo officer and the crane operator gets the container along with a bunch of information and puts it on the ship. The container owners trust that they will do the right job. The same does Kubernetes. It gets pod definition from the user and tries to find the best place in the cluster for it to run. To be more precise, Kubernetes consists of a bunch of elements. In general, it follows the master worker architecture. On the master, there is a central component called API server that receives requests for pod creation, deletion, queries about status updates, and many more. API server stores its object in a highly consistent key-value distributed database called etcd. There is a scheduler that tries to find a node for a newly created pods, and nodes that have an agent called kubelet that is waiting for a scheduler decision. Kubelet is also responsible for starting and stopping pod containers when needed. Moreover, there is a set of controllers. These controllers allow Kubernetes to work in a declarative way, based on the user-provided API object I will explain in a moment. The controllers are trying to execute some actions to move the current state towards the desired state, so that the Kubernetes administrator can focus more on what he wants to achieve instead of individual steps that need to be taken to get there. For example, replica set controller makes sure that there is always the desired number of pods up and running. For example, we may want to have these 5 replicas of Justin Bieber image serving pods in the cluster. If one of the nodes that runs them crashes out of chain, replica set will start the pod on some other node. The same applies to backend and frontends. We want at least a couple of them because, we want our site to be popular and we want to be fault tolerant. Oftentimes, you have to update the version of your software. Usually, you don't want to update everything at once, but slowly roll out the new version, making sure that all of the new pods are started properly. And if they don't, you want to stop and to roll back to the previous version. In Kubernetes, it is handled by deployment controller and deployment object, built on top of the previously described replica set. Okay, so we have a couple of front ends, couple of backends, each with different kind of random IP. How to configure the stuff so that all front ends can talk to all backends? Kubernetes has the answer: services. In our example, backend service creates yet another IP addresses that is automatically round-robin across all backend pods. To make things even easier, Kubernetes registered it in an in-cluster DNS server so that the frontend can talk to backends using a convenient name address. In our gossip sites, there will be 3 services, grouping frontend, backend, and image servers. What about the outside world? To translate HTTP, how to translate the HTTP requested services? Ingress objects, and obviously ingress controller, will make sure that your level 7 load balancer, should it be Google Cloud Load Balancer, Nginx or agent proxy, knows where to forward the request for images or web pages. Okay, so here is how the whole thing looks with Kubernetes. Traffics from the load balancer get to the services, both serving images and frontend. Then the traffic from the services is routed to one of the pods. Traffic from frontend goes to the backend service, and again it is a load balance across all the backends. Backends talk to this database service. And for database, we have a special thing called stateful set. But unfortunately, due to the time constraints, I won't cover it today. So we have all of the components in place running. Now what? In the perfect world, that would be it. But unfortunately, from time to time, you need to check whether all of your stuff is fine, or to debug some issues, or check the client complaints. First of all, Kubernetes provides you with a mechanism to implement health checks for your containers, like liveness and readiness probes. If the liveness probes, the container is automatically restarted, and unready pods are not included in the services. So Kubernetes will not push this traffic to pods that are not yet fully started. There is also a simple mechanism to get basic metrics like CPU or memory consumption from arbitrary pods, as well as logs, or to get to arbitrary container by firing a remote shelter. And if all of that is not enough, there is a number of products well integrated with Kubernetes that can give you more insight into what's in your pod, like Datadog, Alg Stack, InfluxDB Stack, Prometheus, Splunk, Stackdriver, Sysdix, and many more. Okay, everything is up and running and their gossips are available to the user. You thought that 4 replicas of your image server would be enough. But then, some Russian top models does crazy thing on the top of skyscraper in Dubai. Her photos go viral and bang, your traffic skyrockets. What then? Kubernetes can automatically start new pods should the CPU usage go above your desired level. And if you are running on the cloud, like AWS, Azure, or Google Cloud, Kubernetes will automatically get you more nodes to run these pods, if needed. Okay, my time here is slowly going to an end, and I would like to give you a brief update where we are with this project. So, right now the main repository contains about 45,000 commits from 110 different users. It's in the very, very top of GitHub projects. We have contributors from major companies like Red Hat, IBM, Intel, Huawei, Fujitsu, Hitachi, and users with big names. Yahoo, Box, eBay, New York Times, Samsung, Goldman Sachs, and the company that brought you Pokemon Go last year. And if you want to get more information, here is the link to the Kubernetes site. All of the Kubernetes source code is available on the GitHub. And should you have any questions, please go to our Slack channels, kubernetes.slack.com. Okay, thank you. Questions?
I guess the only question will be, does Google use Kubernetes in production, or it uses only the working? Because it seems like it's an open source, but do you really use it, or it's just like a promo?
No, it's not promo. We have an internal project running on Kubernetes. I cannot tell you which one, but definitely we run them internally, plus we offer a paid service on top of Kubernetes.
So Google is a huge adopter of Kubernetes itself, right?
Yeah.
Okay, so the second question, I guess, which modules are different in Kubernetes in comparison with Borg? Yeah.
Oh, wow.
Just maybe such like a load balancing, maybe how it spawns new pods. Just briefly, just a few examples if you could.
Okay, so I'm not sure what details of Borg can I reveal here. And which details?
Just a few details, you know, in Russia you will not see Borg anyway.
Okay, so many things are different. So, for example, we have only one type of load balancer at Google which is used across the whole company. In Kubernetes, we obviously don't want to focus on a single solution. So, apart from integrating with all of the major cloud load balancer, like the cloud balancer in AWS, Azure, or wherever, we have this ingress objects, which on the other hand integrated with all of the possible ingress solutions, Nginx, AG proxy, and stuff like that. So we focus more on being generic enough than being super specific and maybe a little bit more efficient.
Hello, thank you for this session. It was really interesting. I have two questions. One is about the old school secured environments. I mean that historically, one of the fundamental options to maintain a secure environment was the network segmentation. VLANs, firewalls, and so on. How does Kubernetes fit on this model? Does it really work there, or it implies that all nodes are fully visible without any browser? I don't know.
So the nodes are not visible to the outside world. You can definitely have them behind firewall, that there is no need for these nodes to be visible.
No, I mean that on that graph with the database and backends, some special PCI DSS or otherwise regulated projects need to maintain database on some secret another network segment. How does it fit with the whole Kubernetes cluster?
So by default you don't have network segmentation, but using network plugin you can get some. So Kubernetes network model is quite complicated, and we use various providers like Calico and Offline. You can try to configure all the network segmentation there. Plus, we are working on having an in-Kubernetes support for network segmentation, so you don't need to go to the very details of your network solution provider.
Okay, thanks. And the last question, it's kind of related. How does it work with multi-data centers environments? That scheme which you described, is it only exist in one data center? What are the requirements for the interconnectivity between the data centers for Kubernetes to work?
So you would like to have a Kubernetes cluster spanning multiple data centers?
Yes.
So in general, it is not especially advised to have single Kubernetes service spanning multiple clusters in a distributed region. So if you have one data center, let's say in Moscow, and the other one in Vladivostok, it's probably not the idea to build a Kubernetes cluster on top of these two data centers. But we are working on a thing called cluster federation, which will try to put an extra control layer on top of multiple Kubernetes clusters. So you will have a separate cluster in Moscow, separated in Vladivostok, and an extra control plane that will try to provide you an extra layer of functionality on top of these two data centers. For example, if your Vladivostok data centers will go down, this federation control plane will move your pods to Moscow, and vice versa. Also, it will try to make sure that the data in your, the pod definitions in your data center are similar. It will try to distribute all the config information that may be needed, and so on and so on.
Okay, great, thanks. And if we're talking about not far away data centers like Amazon availability zones, Google availability zones.
Okay, so if you are thinking about AWS availability zones, that is definitely possible. There are small things between them, and if you are not putting, multiple thousands of nodes, then it should be working fine. In general, we support having Kubernetes cluster spanning multiple zones in a single region, and it should work fine without any problems. There are no super tight latency constraints around it. So as long as your ping times are reasonable and you have decent transfer rate between your zones, it should be fine.
Okay, great. Thank you very much.